Hi everyone, welcome back to Modern Portfolio Theory and Investment Analysis. In the last chapter, we talked about a single index model, and in this chapter, we are going to extend it and talk about the multi-index model. Okay, so let's start with some recall. Okay, so we saw that how to calculate the portfolio return given the returns of our individual securities, and we also know how to calculate the variance of the portfolio given the standard deviations and covariances of each security pairs, right? So all of this we know already. We have seen that in the previous chapters, and we also know that we have this simplifying term, which is rho 1 2, which is the correlation coefficient, which is calculated by dividing the covariance with the standard deviations of securities like this. Okay, and so we also know that this is basically just too many of them in the inputs, right? So for every pair of them we need to calculate this thing, and that is just too much work, and that's too many inputs and prediction and everything. It's just too much. So we created a single index model to handle that, right? So in the single index model we have that this kind of assumption that return of an individual security depends on two things, right? So one is the market return and the other is the independent return, which is not dependent on the market, right? So that is basically tied to that particular security, right? So we had this AI and beta I components, and we break down AI into further two components, which is alpha I plus EI, right? So alpha is the expected value for AI, and EI is the remaining things, that is noisy kind of thing that is moving the actual returns ups and down, right? So that's what EI was. And we saw that EI, the expected value of EI is actually zero, because the expected value of AI is captured by this alpha I. So the expected value of this noise has to be zero. And we also had this assumption that for any two security, this covariance between this EI and EJ parts of the two securities is actually going to be zero. So in other words, like if there are two securities, they only move together by market, and everything, basically anything that is correlated in that pair of securities is explained by this market movement and nothing else, right? So this is like, this AI is specifically tied to that security, and so if you take the covariance for that, it will be zero, right? So this is how we denote the variance for EI. This is just a notation, nothing really important here. And if you plug it all these things into this, we get this kind of formula. And we also had this assumption that EI is completely independent of the market, which is the covariance between EI and RM is actually zero. Okay, so this and this were our assumptions. So now let's try to extend it to multi-index model. Okay, so multi-index model, we are going to assume that not everything can be explained by market, and this other part which is like completely dependent on the security, right? So there are other things which are not market, and it is still independent of, still like not completely dependent on this individual security, right? So we still have this, we converted this alpha I to AI and betas to B, and we are going to have more index than just the market index, right? So this CI is still our EI part, equivalent to the EI in our single index model, which is the noise part, and the expected value for that is going to be zero. But so let's say I1 is my market, but then there are other indices which are making stocks move together, but is not completely explained by the market, right? So that's the idea behind having this more indices, right? So we are still going to have this assumption that everything basically is explained by all these indices, and whatever is left over is completely uncorrelated, right? So this CI is the leftover part, and that is completely uncorrelated. That's our assumption. And we are going to assume a similar thing that we assume with CI and the market index, which is the CI is completely independent of all of these individual indices, right? So any IK is completely uncorrelated with this CI. Now what we haven't assumed is this thing. So this was assumption, this was an assumption, but this is not an assumption, that two indices, right? So this, one of them can be market, other things can be, let's say, particular specific to that industry or some economic measure, like what is the, how does the stock depend on the rate of return get decided by the government, and many fundamental things, or maybe just you want to create indices based on the industry or anything. So the point is that all of these indices are independent, right? So this is, it kind of sounds like an assumption, but it turns out that we can actually make it happen by construction. So how can we do that is that, let's say we have say I1 as our market index, right? And so I2, let's say, is my industry index, right? And so obviously the industry is partly explained by the market and partly is explained by the industry itself, right? So I2 is not completely independent of I1, in other words, right? So what I can do is that I can write I2 as my single index model, like as a linear function, which part of which is dependent on the market, which is, let's say, it's a gamma 1 times I1 plus some gamma 0, right? So part of which is specific to that industry and the other part is specific to this that moves together with the market. And then if you do some algebra and then like just move around with those gammas and everything, so your BIs and AIs will change, but you will still get a linear expression which has this AI, something that depends on RM, which explains everything that is related to market, and the other part, which is I2, which is leftover part, which is not explained by the market index, right? So this, the other part, gamma 1 part, is, that is, let's say, is explained by the market, and gamma 0 was not explained by the market. So this will have beta and gammas which are not explained by this market, right? So you'll have I2, which is completely independent from I1, and of course your betas, your Bs and As will be different. But yeah, overall you can achieve this kind of effect where the covariance between any two indices is actually 0, right? So I'm not really getting into the details of the math any more than what I just described. So if you want, you can work out on this, but it's not that important. The point is that it can be achieved by construction, right? So it's not an assumption. That's the important point. Okay. So let's calculate the returns for this multi-index model, right? So it's basically like the same things that we did with the single index model, which is that if you want to calculate the average return, then we just basically calculate this average return for these individual indices, and that's it, right? So this is precisely the same thing that we did with the single index model. You want to derive it, you can derive it on your own. It's very easy. Same thing we can derive with for this sigma square. And so that is also, the formula is very, very similar to what we had in our single index model, right? So we had this beta I square times sigma square m and sigma square ei, right? So we just added the other indices like this over here, and that's it, right? So if you actually derive it, you will come to this kind of derivation formula. Okay. And finally, the covariances, it is also kind of very, very similar to what we derived in the single index model. And this is how it will look like in the multi-index model, right? So again, I'm not going into the details of the derivation, but it's trivially easy. You can do it on your own. So it's basically like it is still, everything is still simple, right? So the only problem is that our number of inputs is more, because like we have more indices, but it's still linear, right? So it is still not quadratic. Okay, so it is still like more inputs than having just one index. So let's try to see if we can address that, right? So one of the model for having this kind of multi-index model is called industry index model. So where I'll say one of my index I1, let's say, is my market index, and the other indices are my individual industry, right? So I2 maybe, let's say, the tech industry, I3 maybe something like, say, healthcare industry or things like that. Okay, so my stocks return is explained partly by its own component, which is AI and CI, partly by its the overall market, partly by its how the healthcare industry is moving, how the tech industry is moving, and all those things, right? So this is like a different industry index model. Now, there are companies which kind of do things which span multiple industries, right? So for example, let's say Google, it is tech company, it also comes into communications and everything. So it basically affects multiple industries at the same time. But most of the stocks, they only affect one industry. They only belong to one industry. They are not really affected by a different industry. So and what will happen in those cases, if you try to estimate this B's by regression, then you'll find that most of these B's are zeros. So let's say this stock, it belongs to this I2 industry, say healthcare industry, then it might not be very very dependent on the finance industry. So that for that finance industry, that the corresponding b will be zero, like, or not zero, but let's say very very close to zero, right? So most of these b's will be very very close to zero for those kind of stocks, and one of them will be not zero. So what we can do is we can basically reduce our formula to reflect that, right? So we can have this thing like, say, the individual stock, it depends on its own part partly on the market and partly on the industry in which that stock belongs and nothing else, right? So this, all these dots are gone. This I1, I2, I3 up to IL is reduced to this market and that particular industry, right? Nothing else. So two stocks that belong to different industry will have this part different, right? So IK will be some, for one stock it will be I2, and for other stock it might be I3 or something like that, right? So that significantly reduces the number of inputs again. So you only have double the inputs than the single index model, and not like L times more inputs, right? So and let's say how to calculate the covariances for that. So the formula is still the same, like we can, the way we derive it for the multi-index model. It, if we assume this, then the formula reduces to this. And if the two stocks belong to the same industry, then this will be the formula. If two stocks belong to the different industries, then this term, second term, will be gone, right? So that's the industry index model. So what's the point of all of this is that we want to measure like how do they even work well or not, right? So how can we test that, right? So first is how do we test it? So one way to test it is that we can test the how well the correlation is predicted, right? So if we test how well the return is predicted, then we will not get any information, because we just break down the return into multiple parts. So the predicted return between single index model and multi-index models or different indices models will be roughly the same, but the correlations that is something that is predicted, that's where we reduce the number of inputs, that will be significantly different from whether we are considering one index or multiple index, and in case of multiple index, which indices we are considering. All of those depends on that, right? So one thing is that we can test the correlation, and the other way of evaluating thing is by economic measures, right? So what we do is we, based on the we basically do this predictions for correlations and everything, and based on that we construct the portfolio, right? So we design our portfolio, and then we measure the return for those designed portfolio, which will be different for different multi-index models and single index models and everything. So we just directly check the returns of that constructed portfolio in the future, right? So that's the other way of measuring this thing, right? So that's the economic way of measuring how well this multi-index model is good or not, and all those things, right? So then a lot of people came and calculated all those things, and turns out that this added indices was degrading the performance. The single index model did better than not having the single index model, and it turns out that once we started adding more indices to the single index model, particularly the industry index model, it started degrading the performance. So it was basically adding more noise than it was bringing more benefits, right? So that was the reason for this degradation in the performance. Okay, so that's one thing. And then it turns out that if you recall that we had this assumption, right? So that the stocks basically the CI parts, right? So the non-explained part basically move together, right? So even in the single index model, we had this EIEJ is equal to 0, expected value of this EI is equal to 0, and that is obviously not true for most of the practical scenarios. So if we try to measure that stocks which are let's say, forget about the actual industries, let's say there are stocks which partly are just, if their movement is partly justified by the market, they are moving together, and there are parts which are not explained by the market and they're not tied to that industry. And so based on that, if we group those stocks together, right, so that basically creates something called pseudo industries, the industry that is observed in the stock returns and market and portfolio performances, but it is not actually like categorized into specific industries that we have designed as humans, right? So it may not be like healthcare and finance and all those kind of industries, but there are still groups inside the overall set of stocks in the market that basically is called a pseudo industry, right? So if we try to construct indices based on those pseudo industries, then it turns out the performance is improved, right? So on both measures, right? So it predicts its correlations better, and the design portfolios give better return, right? So that's where the advantage of multi-index models comes into the picture. And even in this case, this always part is not true, right? So on an average it improves, but it is not always true. So there are cases in which it is degrading performance as well. There are like the overall portfolio is not completely dominated by the multi-index model, right? So that's something that to keep in mind. Okay, so then people came up with something called average correlation model. So let's see what that is, right? So it's basically like, say, we are trying to predict correlations, right? So let's say not predict them at all, and say new correlations between any two stocks is predicted like this, is basically an average of all the correlations we have observed so far between any pairs of stocks, and that's basically the new correlation for any pairs of stocks. So basically it is same correlation coefficient for every pair of stocks that we have in the market, right? So it's called this overall mean model. So it kind of sounds like complete nonsense from the practical perspective, but in terms of research perspective and theoretical perspective, this is like a baseline. So everything should be able to do better than this, right? So then people created this something like based on that they try to improve it and said let's consider something called traditional mean model, which is like we are going to assume that the correlations between stocks are same for the stocks which belong to the same industry. Let's say there are two stocks which belong to, say, healthcare industry. So what we do is that their correlation is basically same as all the stocks in the healthcare industry, and we see what is the average correlations between all the stocks in that healthcare industry. And so that's the correlation, that's the prediction of the correlation between any two stocks in the healthcare industry, right? So it's basically the same for every two stocks in the same industry. And it turns out that very surprisingly that both of this do better than single and multi-index model, right? So it kind of in some sense sounds like the single and multi-index models are very well designed and very well constructed and everything, but when it comes to predicting the markets, they are not that good as this completely nonsensical sounding models. So multi-index model is already introducing a lot of complexity. So it in many cases it is helpful, like we saw previously that in the pseudo industry index model, right? But it still like requires a lot of work to figure it out when it is better than something which is very, very trivial. Okay, so I think that's all for this chapter, and we'll see you in the next chapter, right? So where we will discuss how to calculate the efficient frontier again using the single and multi-index models and everything. So if you haven't subscribed already, please subscribe. It will help me out, and you'll get notified whenever I upload the recordings for the new chapters.